So question number 7 of PMI exercise is here. The question is, show that 1 into 3 plus 3 into 5 plus 5 into 7 and so on. The last term is this 2n minus 1 into 2n plus 1 equals to, you want to show that n into 4n square plus 6n minus 1 by 3 with the help of PMI. So let's try this here. What we do first we prove for n is equal to 1 as we know here. So for n equals to 1 here, what is LHS? You know, left hand side is put 1 here, so this will be 1, put 1 here, so this is 3, so 1 into 3, so first term alone 1 into 3, which is 3, which is LHS here, that is LHS 3. Go for RHS. What's RHS? Put here 1, so 1 into 4, 1 square plus 6 minus 1 by 3. So 10 minus 1, 9 by 3, which is 3. So LHS equals to RHS here. And therefore P of 1 is true. Now next step, you know, that's your assumption part. We prove, this is our assumption part. We assume that P of K is true. This is our assumption. That is, let's write the meaning of it. That is, what is the meaning of it? Instead of n, you put k in this statement here. So I'm putting instead of n k. So you have 1 into 3 plus 3 into 5 and so on. Here 2k minus 1 into 2k plus 1 equals to their k. So we have here k into 4k square plus 6k minus 1 upon 3. This is just 1. Okay. Now the next important part is, you know, that proving part. So now we prove that P of k plus 1 is true. This is what we show. We show that the P of k plus 1 is true. This was the assumption part. Now this is proving part, remember. So with the help of 1 we are going to prove, you know, here. So let us start with LHS here. What is LHS? That is, instead of n you put k plus 1. So 1 into 3 plus 3 into 5 and so on here. Instead of n, k plus 1. So 2 into k plus 1 minus 1 into 2 into k plus 1 plus 1. Now what will prove, right? That should be there in your mind. So we show that in this RHS, this is what we need to show here at the end. Here, instead of n, you must have k plus 1. So k plus 1, 4 into k plus 1 whole square, 6 into k plus 1 minus 1 by 3. Right? That's what you want. So we keep this much in our mind, remember. Okay. So here, now our normal procedure, you know, 1 into 3 plus 3 into 5. What we do? Here, I write your last term simplified. 2k plus 2 minus 1, that is 2k plus 1. 2k plus 2 minus 1, which is 2k plus 1. 2k plus 2 plus 1, so plus 3 here. Just have simplified here. 2k plus 2 minus 1, 2k plus 1, 2k plus 2 plus 1. Now previous term. This is k plus 1th term. Previous term means always this, you know. So 2k minus 1 into 2k plus 1, that you know. Now you simplify this much here. We put the value of this much from 1 and then we'll simplify. So by 1, what we are getting? This is equals to k into 4k square plus 6k minus 1 upon 3, and the last term as it is 2k plus 1 into 2k plus 3. Fine. What I did, because of 1 I have placed the value of this underlying expression. That's what always we did in all questions of PMI. Now just algebraic thing, you simplify this carefully here, and you see that you must get like this. I'm just concentrating here. You must have like this k plus 1 inside the bracket 4 into k plus 1 the whole square, 4 into k plus 1 the whole square plus 6 into k plus 1 minus 1 the whole by 3. You need to get this, remember. This you need to get. So just simplify this. The simplification is not a big task, it's simple algebra. And this is your RHS, remember. I leave this much for you. This is your RHS. And therefore, you can say that by PMI, given statement Pn is true for every n, is true for every n belongs to n. Right? So therefore, the above statement, this statement is always true for each integer, positive integer n, remember. Okay, that's one. Question number 8 here. Let's prove this by PMI. So in this question, Pn is 1 into 2 plus 2 into 2 square and so on. N into 2 raised to n equals to 1. You want to show that n minus 1 into 2 raised to n plus 1 plus 2. Remember, this is what you want to prove. So first, as you know, prove for n is equal to 1 here. So for n equals to 1 here, for n equals to 1, what is LHS? Put n equals to 1 on the LHS. If I put 1 here, 1 into 2 raised to 1, that's the first term alone, which is 2. What is RHS? Put 1 there. If I put 1 here, this is 0. Plus 2 is already there. So this is 2. So LHS equals to RHS, and therefore P1 is true. Therefore P of 1 is true here. Okay. Now next step, that's our assumption part. We assume that the P of k is true. We assume that the P of k is true, where k is any natural number, you know. So what's the meaning of this? In the statement, instead of n you write k. So 1 into 2 plus 2 into 2 raised to 2 and so on, k into 2 raised to k equals to k minus 1 into 2 raised to k plus 1 plus 2. This is 1, as you know, as we did everywhere. Okay, now the proving part. So next is we prove. What we are going to prove? We prove P of k plus 1 is true. P of k plus 1 is true. That's our proving part. We show that the P of k plus 1 is true. So in this statement, here we start with this, but instead of n you are going to write k plus 1. 1 into 2 plus 2 into 2 raised to 2 and so on. K plus 1 into 2 raised to k plus 1. Right? We have started with this. What we prove, that should be there in your mind. Here, after the simplification, you must have this one, but instead of n you must have k plus 1. So k plus 1 minus 1, that is just k, into 2 raised to k plus 1. So k plus 1 plus 1, k plus 2 plus 2. This will get cancelled. So you just need this much, remember. So this we keep in our mind. This should be there in your mind, remember. I did nothing. Instead of n, I have placed k plus 1, right? Okay, so with this information now we just simplify. So first step is you write the previous term here. Last term is k plus 1, 2 raised to k plus 1. Previous term k into 2 raised to k. This much you know by 1. What is this by 1? This is equals to k minus 1 into 2 raised to k plus 1 plus 2, this is by 1, plus k plus 1 into 2 raised to k plus 1. So here reason is because of 1. Okay, now here we just need to simplify. That plus 2 remains same because on the RHS you need plus 2, as you know here. You need plus 2. So we'll do nothing with plus 2 here. So plus 2 as it is here. From these two you take 2 raised to k plus 1 common. So here you will get the k minus 1 plus k plus 1 plus 2 as it is. This 1 will goes away. This would be just 2k. So 2k into 2 raised to k plus 1 plus 2. So this would be here 2 into, this is k plus 1 and 1 power from here. So k plus 2 into this k as it is plus 2. Now you already noted that this is just your RHS. In this statement here, instead of n, you put k plus 1. So k plus 1 minus 1, that is k, as I've shown here. It is this much. You see, you are getting same. So therefore you are getting RHS here. Therefore, what is your conclusion? Therefore, you can say that the P of k plus 1 is true. And therefore, the PMI says, so by PMI, by principle of mathematical induction, Pn means given statement is true. Always true for all natural numbers. This is by principle of mathematical induction. PMI says that the given statement must be true for all natural numbers. Next, question number 20th. You want to show that this is divisible by 11. 10 raised to 2n minus 1 plus 1 is divisible by 11. Means it's a multiple of 11. So for n equals to 1, let's put n equals to 1 here. So you have 10 raised to, if I put 1, 2 minus 1, that is 10 plus 1, which is 11, is divisible by 11, you know. Divisible by 11. Every number is divisible by itself. That's 1. Then assumption part. What is your assumption part? Assume for n equals to k. So we assume that this is our assumption part. P of k is true. Sorry, here I should write therefore P of 1 is true. I forgot to mention this. Let me write therefore P of 1 is true. Now we have assumption part, that is P of k is true, where k belongs to n. So we have here 10 raised to 2k minus 1 plus 1 is equal to 11m. If I put n is equal to k, this is divisible by 11, so 11m, for m belongs to n. Okay, we call this as a question number 1 and we keep it inside. We did such questions earlier also, so I hope this is clear to you. It's divisible by 11 means it's a multiple of 11, that's 11 into something, we keep inside. Now we have proving part. We prove P of k plus 1 is true. that is here we need to start with LHS. So here LHS is this 10 raised to 2k plus 1 minus 1 plus 1, and we'll show that this must be multiple of 11, that is 11 into something, right? That's what we need to do. Okay, so if I simplify this little bit, this is 10 raised to 2k plus 2 minus 1, so plus 1 plus 2 minus 1 plus 1, and then here down plus 1. Now if you remember earlier questions, we need to use 1 here, but there you have 10 raised to 2k minus 1. So what I'll do, I'll express in that form, 10 raised to 2k. If I write minus 1, I need to write plus 1, so plus 2 plus 1. So you have 10 raised to 2k minus 1 into 10 square plus 1 as it is. What I did here, just have expressed 2k plus 1 in 2k minus 1 form. Why? Because I want to use the equation number 1. Okay, so for equation number 1, I need to express in this form. So I wrote here minus 1. If I write minus 1, I need to write plus 1, but plus 1 is already there, so it becomes plus 2. This is same as this, you can see. Now this much you know by 1. What is that? By 1, it is 11m minus 1. You look at it by 1 there. I'll write here by 1. Here by 1. 10 raised to 2k minus 1. I wrote 11m minus 1. So here you have 11m into 10 square minus this 10 square plus 1. So 11 into m into 10 square, which is 100. This is 99 plus 1, so minus 99. And now you can find 11 common from this. So 1 into 10 square, which is 100 minus 9, whatever it is, but this is some constant. I'll call that as m dash. So 11 m dash. What is m dash? It is some constant, remember. What is that value? It's not important, but it is 11 into some constant. So therefore, you can say that if I put instead of n here k plus 1, this number is divisible by 11. And therefore, here if I write, we can say here p of k plus 1 is true. And therefore, by PMI, by principle of mathematical induction, by PMI, Pn is true. Pn is true for every natural number. This is what the proof by PMI. That means the given statement is always divisible by 11 for every natural number. That's what the principle of mathematical induction, and here it is a proof. Question number 21. X raised to 2n minus y raised to 2n is divisible by x plus y. That means this is a multiple of x plus y. Divisible by x plus y means this expression is multiple of x plus y. So for first n equals to 1, we have x raised to 2 minus y raised to 2. You know factors, that is x minus y into x plus y. And this is obviously which is divisible by x plus y, divisible by x plus y. So therefore p of 1 is true. That's one thing. Now next is assumption part. We assume that p of k is true. That is, if I put instead of n k, it is multiple of x plus y. So x raised to 2k minus y raised to 2k equals to x plus y into some constant m, where m belongs to n. It's divisible by x plus y means what? It's a multiple of x plus y. So we have this here. Okay. Now the next important part is for n equals to k plus 1. So we prove now p of k plus 1 is true. So instead of n, what you are going to take? K plus 1. So here the expression is x raised to 2 into k plus 1 minus y raised to 2 into k plus 1, and we'll show that this is also x plus y into some constant. It may not be m, something else, but it would be multiple of x plus y with the help of, let me call this as 1. Okay, so I'll rewrite as x raised to 2k plus 2 minus y raised to 2k plus 2. Okay, now obviously there is no other option. You need to use this equation 1. So what I'll do, suppose I want to put the value of x raised to 2k. So I'll write like this: x raised to 2k into 2 square, and y raised to 2k plus 2 I'll keep as it is. You can put the value of y raised to 2k also, remember. This is 4, I'll write here. What is x raised to 2k? Look at it, equation 1. It would be x plus y into m plus y raised to 2k minus y raised to 2k plus 2. This is because of 1, remember. This is because of 1. That's always useful equation, you know. What I did, anyone you can put, the choice is yours. What I did, I started with n equals to k plus 1. X raised to 2k I've expressed in this form. Why? Because I want to put x raised to 2k. Okay, and what's the value of that? X plus y into m plus y raised to 2k. Now we just simplify, and you will see that you will find x plus y factor from this, that you will notice. So let's simplify here. So 4 into x plus y into m plus, this is 4 into y raised to 2k minus this one y raised to 2k into you can write here y square. So here I think, I'm sorry, this is my mistake. This is not x square as 2 square. It should be x square, x raised to 2. So here it is x raised to 2. So this is x raised to 2. If I open the bracket, this is x raised to 2, I mean x square. Fine. I think this is fine now. This was the little mistake. I wrote 2 square. It's not 2 square. It is x raised to 2k into x raised to 2. So it is x square. Here also x square, and then I open the bracket. Okay. Now in this term you are already having x plus y. Let me copy this: x square into x plus y into m plus, what's common in this 2? Y raised to 2k you will find common. So you have x square minus y square, and you know it has 2 factors. Okay, so finally the next step would be here. This is your next step over here. That is x square into x plus y into m as it is, y raised to 2k into x minus y into x plus y. Now you can find x plus y common. So you have x square into m plus y raised to 2k into x minus y. Now whatever it is, but it is some constant. So we call that as m dash. And therefore, if you just look at it beginning here, you had started n equals to k plus 1. You had started with this, and you have shown that it is x plus y into m dash. So therefore you can say that the p of k plus 1 is true, and therefore finally by PMI you can say that by PMI Pn is true, Pm is true for all n belongs to n. The statement is true for all natural number. This is always true. Question number 18, which is about that inequality, 18 and 24. Okay, so let's see the 18. We call that as P of n, which is 1 plus 2 plus 3 up to n. It is always less than 1 upon 8 into 2n plus 1 the whole square. You want to show this. So first step is procedure is same. For n equals to 1. So if you put 1, LHS is just 1, this one alone. What about RHS? 1 by 8, put 1 here. So 3 squared, it is 9. So 9 by 8, which is 1 point something. So obviously this is greater than 1, and therefore P of 1 is true. Next step, our assumption. So we assume that the P of k is true. We assume that P of k is true. Therefore, we have 1 plus 2 plus 3 up to k is less than 1 upon 8 into 2k plus 1 the whole square. You call this as equation number 1. This is our equation number 1. Now we prove that the statement is true for k plus 1. So we prove P of k plus 1 is true. This is what we want to prove. So we start with this. Instead of n, you are going to write k plus 1, and we'll show that it is less than that RHS expression. So I'm starting with this 1 plus 2 plus 3 plus last one is k plus 1. We'll show that this is less than, put here k plus 1. So it should be less than 8 into 2 into, what is this, k plus 1 the whole square. So this is 1 upon 8 into, this is 2k plus 3 the whole square. We want to show that this is less than this. What I did, just I will notice what we want on the other side instead of putting n equals to k plus 1. So I have this much in my mind that I need this one on the right hand side, remember. Okay, so let's write here up to kth term. Last term is k plus 1. What's the previous term? It is k. It is always this, you know. Now you know by 1 this is less than, not equals to, remember. So here your less than sign. This is very important point, remember. You are not, usually in all earlier examples you had equal to, here you have less than. So this is less than 1 upon 8 into 2k plus 1 the whole square plus the last one, which is k plus 1. Okay. Now we just simplify and we notice that whether it is this or not. Okay, so let's see that. So now we are simplifying this. So if you take LCM here, 1 upon 8, if I expand this, 4k square plus 4k plus 1, 8 will multiply with this, so plus 8k plus 8. These two are equal, remember. But this is bigger than this expression, remember. That's so inequality would be there. Now what is this? 4k square, 8 plus 4, 12k plus 9 by 8. And now this is nothing but 1 upon 8 into, this is the perfect square, which is of what? 2k plus 3 the whole square. And that's what you wanted, remember. This is same as 1 upon 8, 2 into k plus 1 plus 1. Okay? That's what you want. In this expression, instead of n, you must have k plus 1. Right here, instead of n, you must have k plus 1. That's what I've shown here, and that is what you are getting here. That is same as this, which is same as this. And therefore, you can say that here p of k plus 1 is true. P of k plus 1 is true. And therefore, by PMI, given statement Pn is true. Pn is true for every n belongs to n. So the statement always holds true. That means this is always less than this number. Now you have shown that this statement always holds true for every natural number. So if you put any n, this would be always less than this. We have proved now by PMI. One more inequality question, 24th number. 2n plus 7 is less than n plus 3 whole square. So for n equals to 1 here, what is left hand side? 2 plus 7, which is 9. What about this? 1 plus 3, 4 square, which is 16, and it is obviously bigger than 9. So therefore, P of 1 is true. Now our assumption part. So we assume that P of k is true. This is our assumption part. We assume that the P of k is true. That is, in this statement, instead of n you put k. 2k plus 7 the whole raised to k plus 3 the whole square. Okay. Now we go for proof of k plus 1. So let's prove that. So let me write here. We prove that P of k plus 1 is true. We prove P of k plus 1 is true. This is what we want to prove. So on the LHS, I'll just take, instead of n, k plus 1. Let me start with this here. 2 into k plus 1 plus 7. And here, instead of n, I must have k plus 1. So k plus 1 plus 3 whole square. This is what you want on the RHS, remember. You want to show that this expression is less than this much, k plus 1 plus 3 the whole square, which is same as k plus 4 the whole square. You want this, so we keep this much in our mind, remember. Okay, and we'll use this equation number 1, remember. This is what I want. I wrote what I want first. Okay, now here, if I simplify, this is 2k plus 2 plus 7. But I know 2k plus 7 is less than this. So 2k plus 7, let me write in one bracket, plus 2. Now 2k plus 7, this much, by 1 is less than k plus 3 the whole square, and plus 2 as it is. Now if you simplify this, what is this? This is k square plus you have 6k plus 9 plus 2, which is 11. Fine. Now let me drop right now this we keep in our mind. Okay, now here I want k plus 4 the whole square. What is k plus 1 the whole square? Which is k square plus 8k plus 16. So what I'll do, k square plus 6k plus 11 is there. To get this, I need this much extra, so I'll add this. How much I need to add? 2k and 16, so plus 5. I have added this much. So you can write here, adding this much on the RHS, adding 2k plus 5 on RHS, right inside. Remember, I have added, I have not subtracted, remember, just I am adding. So this will be bigger than this, remember, that's why you have this inequality. You are not writing equality. Now what is this? This is nothing but the k square plus 8k plus 16, and that is nothing but what? K plus 4 the whole square. That's what you wanted. You wanted k plus 1 plus 3 the whole square, that is k plus 4 the whole square. So what you have shown finally, 2 into 2k plus 1, 2 into k plus 1 plus 7 is less than k plus 4 the whole square. Right? So in the above statement, instead of n, now it become k plus 1. You can see here. Instead of n, it become k plus 1 now. So therefore, as we wrote everywhere, p of k plus 1 is true. And therefore, by PMI, Pn is true for every n belongs to n. So the statement is always true. The given statement is always true. You can put any n, the statement would hold true. Fine, that's a proof.